Greetings everyone, and welcome to my next video in my lecture series on applied differential equations. So we are solving homogeneous systems of DEs, linear DEs, and we're looking at the case where we have repeated eigenvalues, but we have enough eigenvectors. The geometric multiplicity of the eigenvalues is equal to the algebraic multiplicity. So let's work on an example. We're going to solve vector x prime is equal to this matrix times vector x, where we're looking at a 3x3 system. So let us get started with this. For our answer, I was going to change colors. For our answer, recall that, so here's this entire matrix is going to be matrix A. Recall that for either upper triangular or lower triangular or diagonal matrices, upper triangular is when all the elements are either along the main diagonal or above it. Lower triangular is when they're on the main diagonal or below it, or diagonal is when they're only on the main diagonal. These matrices have a very nice property, which is that the eigenvalues are equal to the diagonal entries. And so from that, we can conclude that our matrix A has the following eigenvalues. It has 1, 2, and 2. And I write the 2 twice to draw attention to the fact that it happens twice. So we've got a repeated eigenvalue here, and the algebraic multiplicity of lambda is equal to 2. Is equal to 2 because it occurs twice in our list when we write them all out. Lambda 2 is 2. The algebraic multiplicity of lambda is 1 here. And so now we need to find the eigenvectors. So we're going to get let lambda 1 is equal to 1. And we're trying to find all the eigenvectors here. So we get a minus lambda I onto k is equal to 0. And basically what we're going to do is we're going to subtract 1, which is lambda, from all of the diagonal entries. That means that what was 203 before becomes 103, the top row. And then it was 020, so it becomes 010 because we're again subtracting 1 from each of the main diagonal entries, and 001. Oh, and we're let's write the augmented matrix here, because that's equal to the 0 vector. Oh, I should write the 0 vector there. And I'd like you to notice that this one's actually kind of nice because it's already in RREF. And we don't have to take any further action there. Z is our free variable. Oh, wait a minute. That bottom entry here should have been 0. Sorry, I was not paying attention. So this is already in REF. If it had been a 1 there, as I had written, it wouldn't have been in REF. And Z is our free variable. So we're now going to let Z is equal to T. Then X, Z is equal to T. Then our X, what am I doing here? Wait a minute. I'm going to totally scrub this and go back. So we had 203, and we're going to change all of the diagonal entries to be subtracting 1, so we get 1, 1, and 0, and then the remainder remains the same. Okay, that's much better. It's a nice when I actually know what I'm doing. And read my notes. So we're going to let Z equal to T. Then the top row says that X plus Z plus 3Z is equal to 0. And so that means that X is going to be negative 3T. Y is just going to be 0 here. And then K is going to be negative 3. And then Y is going to be 0, and Z is going to be 1. And let's call this k sub 1. So that is the eigenvector for the eigenvalue 1. And now we're going to let lambda equal our repeated eigenvalue 2. We get a minus lambda I is equal to 0. Let me try to do onto k is equal to 0. Try to do a better job this time of actually writing it out. I'm going to now subtract 2 from all the main diagonal entries. I'm going to get 0, 0, and -1. The remaining entries will look the same as before. Try to line them up a little better here. And this is not in REF, but you can see that going to REF will be really fast. Get a pretty featureless matrix that only has one non-zero entry in it. Top row divide by 1. Take with the bottom row multiplied by 3 and add it to the top row. And so here our x and y are free variables, so we're going to let x equal s and y is equal to t, and we find that z is going to equal to 0. And then our k is going to be s, t, and 0. And so if you write it in terms of our parameters s and then another vector onto parameter t, you get 1, 0, 0 and 0, 1, 0, where the column vector out front of s is one of our eigenvectors rather. It's so k2 is equal to 1, 0, 0, and k3 is equal to 0, 1, 0. Now notice here that the eigenvalue 2 was repeated. It had an algebraic multiplicity of 2, but it also has 2 eigenvectors, and so its algebraic and its multiplicity is equal to, its geometric and algebraic multiplicities are the same. So geometric multiplicity, the number of vectors, is 2, and that's equal to the algebraic. And that's helpful to know. We have enough eigenvectors. And so we can write then that capital X is equal to the sum of c sub I vector k sub I e to the lambda it is equal to -3, 0, 1, whoops, c1, forgot the c1, e to the t, plus c2 onto 1, 0, 0, e to the 2t, plus c3, write a better 3 here, onto 0, 1, 0, e to the 2t. And that is our solution.